it is, pausing just long enough to create the impression that relief has arrived. Across the lower deserts, temperatures are forecast to dip slightly through the middle of the week. After days of extreme heat, even a small decline can feel like the atmosphere is finally broken. The maps begin changing, and thunderstorms return to parts of Arizona. Moisture pushes north. Clouds appear over mountains that spent the previous week beneath a hard blue sky. Then the forecast turns in the opposite direction. National Weather Service Phoenix says temperatures fall only slightly through Wednesday before climbing again late in the week. Extreme heat warnings remain in effect across the lower deserts through Friday, while higher humidity makes the air feel even hotter. Major heat risk continues, and parts of the region can return to extreme heat risk as high pressure strengthens again. That is the real story behind the deep red map. The color does not represent one new disaster replacing the heat wave. It represents heat risk remaining dangerous while the atmosphere changes around it. The original title, therefore, needs a direct correction. This heat is ending is not supported across the southwest. And the current forecast shows a brief easing followed by renewed warming. What replaces it is also too simple because several hazards overlap. Humid heat, warm nights, thunderstorm outflow, blowing dust, lightning, localized heavy rain, and flash flooding. And the strongest defensible title is this. The southwest heat is easing briefly. Then humidity pushes heat risk deep red again. The word heat risk matters because red can mean many different things on a weather map. A red heat risk area represents major risk with potential impacts for much of the population. Magenta represents extreme risk when long-duration heat and limited nighttime recovery can affect the entire population. A red flood outlook means something else. A red flag warning means something else. A red flag warning means something else. A radar image can also contain red, but that color represents estimated precipitation intensity or velocity rather than a regional impact category. The color catches attention, and the label tells the truth. As of the evening of August 3rd, the Phoenix forecast still showed well above normal temperatures, scattered major to extreme heat risk, and lower desert apparent temperatures near 110 to 120 degrees as moisture increased. In the same forecast expected storm chances to remain focused mainly over higher terrain through much of the week before becoming more favorable across lower deserts toward the weekend. Southern Arizona had already begun showing the other side of this transition. A flood watch covered areas around Tucson, Nogales, Sierra Vista, and nearby mountains until late Monday evening. Forecasters warned that strong thunderstorms could produce heavy rain, blowing dust, and powerful outflow winds. Most storm-affected areas were expected to receive roughly half an inch to 1 inch, while isolated locations could receive between 1 and 3 inches. That does not mean the entire Southwest was turning into a flood emergency. It means one part of the region was moving into monsoon hazards, while another remained under extreme heat alerts. The map became more complicated because the weather became more complicated. For documentaries that separate the strongest headline from the most accurate mechanism, subscribe and stay with us. The important question is not what single hazard replaces the heat. It is why the atmosphere can become stormier without delivering reliable relief. Then return the heat risk to deep red only days later. The mechanism begins with the subtropical ridge. During a major southwest heat episode, high pressure in the middle and upper atmosphere encourages air to sink, and as that air descends, it compresses and warms. Clouds become harder to sustain. Sunlight heats the ground, and the same circulation can remain in place for days. The ground stores that energy. Asphalt, concrete, roofs, rock, and dry soil absorb heat through the afternoon and release it slowly after sunset. And when nights remain hot, homes and bodies lose the recovery period that normally reduces stress before the next day. A slight drop in afternoon temperature does not erase that stored heat. It can also arrive with a trade-off. As the ridge shifts, moisture from Mexico, the Gulf of California, and the eastern Pacific can move north into Arizona and nearby desert areas. The thermometer may fall a few degrees while dew points rise, the air becomes less dry, and sweat evaporates less efficiently. The body keeps more of the heat it is trying to release. This is why a day that is technically cooler can still produce dangerous apparent temperatures. The human consequence is a decision problem when people see a lower forecast high, cancel cooling plans, resume outdoor work, or assume vulnerable relatives no longer need checking. The atmosphere has improved relative to the peak, but relative improvement is not the same as safe conditions. The forecast is not moving from heat to comfort. It is moving from extreme dry heat toward a short period of somewhat lower temperatures, greater humidity, uneven storms, and then renewed heating. And the timing of the warning also matters. A heat alert can remain active through a period of modest cooling because the dangerous episode is measured across days, not from one afternoon maximum to the next. In emergency rooms, cooling centers, utilities, and outdoor workers respond to accumulated exposure. The desert's warmest surfaces also lag behind the atmosphere. A shaded thermometer can drop while walls, parking lots, sidewalks, and vehicle interiors continue radiating heat. People returning outdoors in the evening may feel relief in the air but remain surrounded by surfaces capable of adding heat back to the body. And that lag is part of the false ending because the weather changes first while the built environment cools later. The red map is not the replacement. It is evidence that the heat never fully left. Heat risk was created for exactly this kind of forecast. A temperature map answers one question: how hot will the air become at a specific location? Heat risk asks a broader question: how likely is that heat to create impacts over a full day, including the night that follows? The product considers how unusual the heat is for a location and time of year, how long it lasts, how warm the nights remain, and how much the population has already acclimated. It then places the result on a 0 to 4 scale. Green means no elevated heat risk. Yellow marks minor risk for people who are extremely sensitive. Orange represents moderate risk for people who are sensitive to heat, and red represents major risk for much of the population. Magenta represents extreme risk for the entire population during long-duration heat with little or no nighttime relief. And heat risk also changes by location. A red category in Phoenix is based on local climate and expected impacts, not the same raw temperature threshold used in a cooler city. And this prevents the product from treating ordinary desert summer heat and unusually dangerous desert heat as identical. The result is an impact map rather than a national contest for the highest number. That scale explains why the map can stay red when the daily high temperature slips downward. It is also persistent. A person working outdoors may begin Tuesday already dehydrated for Monday. An older adult may live in a house that never cooled overnight. A power outage may remove air conditioning during the period when the body is supposed to recover. And someone sleeping outside may experience a low temperature that remains dangerously warm until sunrise. The next day does not begin at 0. Humidity makes the problem harder to see because it changes the relationship between the thermometer and the body, and sweat cools the skin when it evaporates. In dry desert air, evaporation can be rapid, although the body can still lose water dangerously fast. When moisture increases, the air accepts less additional water vapor, sweat remains on the skin, and the body must work harder to release the same amount of heat. And this is why apparent temperature can rise even when the actual temperature falls. It is also why the first moisture surge of the monsoon can feel disappointing. The sky changes, clouds build, and the air smells like rain, yet the city may receive little or no rainfall. The humidity arrives before the cooling, and the North American monsoon is not one storm crossing a boundary. It is a seasonal shift in pressure, wind, and moisture transport. Terrain heats unevenly, moist air moves north, and mountains force that air upward, helping thunderstorms form first over higher elevations. Only later do some storms survive long enough or send outflow far enough to influence lower desert cities. The first impact may be wind. A thunderstorm contains rising warm air and descending cool air, and rain and hail add weight to the downdraft. Some rain evaporates before reaching the ground, cooling the air even more. The descending air accelerates, strikes the surface, and spreads outward as an outflow boundary. That boundary can travel far beyond the rain. It can cross a highway beneath a nearly clear sky. It can lift dust from fields, construction sites, dry lake beds, and open desert. It can reduce visibility before a driver sees lightning or rainfall. It can lower the temperature suddenly without ending the regional heat episode. The cool air is shallow and temporary. After the outflow passes, humidity remains, the ground continues releasing stored heat, and the next day begins beneath the same large-scale ridge. This is the hidden reason the weather appears to switch hazards while heat risk stays high. The thunderstorm operates locally, and the heat dome operates regionally. A storm may cool one neighborhood while the broader desert remains dangerously hot. Another storm can send a dust wall into Phoenix but leave the airport with almost no measurable rain. Higher terrain may receive repeated downpours while the lower valley only receives wind and humidity. And flash flood risk is equally uneven. Dry washes can carry water from storms falling many miles away. A road crossing may sit beneath blue sky, while runoff approaches from mountains hidden beyond the horizon. Rock pavement, steep slopes, wildfire burned scars, and compacted soil can accelerate water into channels faster than it can spread or soak into the ground. That does not make every desert surface unable to absorb rain. It means the outcome depends on intensity, duration, terrain, soil, vegetation, and where the storm remains stationary. The current Tucson flood watch illustrated that scale. It covered specific counties and valleys, not the entire Southwest. And forecasters expected widespread strong thunderstorms in portions of south-central Arizona, with isolated places potentially receiving 1 to 3 inches. A watch means conditions are favorable. It does not mean flooding is occurring everywhere. A warning is issued when a more immediate and specific threat is developing or already underway. The difference between those words is as important as the difference between red maps. Heat risk red describes potential heat impacts. A flood watch describes favorable conditions for flooding. A red flag warning describes critical combinations of dry fuels and weather. Radar red describes a measurement inside a storm. And the same visual language can represent 4 different scientific questions. A dramatic thumbnail can easily collapse them into one. The documentary cannot. And the current transition is dangerous precisely because no single map captures it. One layer shows heat risk, another shows thunderstorm probability, and others show flood watches, dust, or fire weather alerts. And the public experiences all of those layers in the same body, on the same road during the same evening. That is the second major refrain. The heat is not followed by weather, the heat becomes the background on which every new hazard arrives. Phoenix experienced a sharp example of this false handoff on August 22, 2024. The afternoon began inside a normal monsoon environment. Moisture and instability were present, but the event did not arrive as one organized wall of rain covering the entire metropolitan area, and several thunderstorm clusters developed separately. At about 4:30 in the afternoon, a storm formed directly over Phoenix Sky Harbor International Airport and produced a downburst with a measured peak wind gust of 64 miles per hour. The storm then moved toward North Tempe and Scottsdale, where another strong downburst uprooted large trees, brought down power lines, damaged property, and interrupted electricity for hundreds of customers. Heavy rain fell in a narrow corridor. Storm spotters reported more than half an inch in about 30 minutes in parts of Scottsdale, producing minor street flooding. A different storm developed over the Ahwatukee Hills and produced its own damaging wind. Before those city storms formed, thunderstorms over Pinal County sent a powerful outflow boundary northwest toward the East Valley. That outflow carried gusts above 50 miles per hour. It lifted a broad dust storm and reduced visibility to roughly 1/4 of a mile in some places. The event demonstrates why storms replace heat is a misleading sentence. One area experienced a dangerous downburst, another received heavy rain, and another saw dust with almost no meaningful cooling rainfall. Power failed exactly when residents depended on air conditioning. The atmosphere changed form, but the human heat burden did not necessarily disappear. Downbursts are especially important in desert cities because their strongest winds can arrive quickly and spread across a wide area. In a storm's rain-cooled air is denser than the surrounding hot air. When that cold pool hits the ground, it moves horizontally, sometimes accelerating through gaps in terrain or urban development. And the leading edge can act like a small front as pressure rises. Wind direction changes, dust lifts, and temperature falls. The sudden cooling feels dramatic, but it can last only a short time. Behind the gust front, the air may remain humid, debris may block roads, and electricity may be unavailable. A neighborhood can move from heat stress to wind damage in minutes, then return to heat stress inside a powerless home. And the power disruption is the bridge between those hazards. Air conditioning demand remains elevated before the storm, while wind and falling trees threaten the system delivering that cooling. And when power fails, indoor temperatures can rise rapidly in buildings with poor insulation or direct afternoon sun. The storm may last 20 minutes, the heat consequence can last for hours. This is the compound hazard the red map cannot show by itself. The August 2024 event also shows why rainfall is a poor measure of storm danger. A dry or nearly dry location can experience the wind generated by a wet storm elsewhere. Evaporating rain can strengthen a downdraft before much water reaches the ground. The strongest outflow can therefore move beyond the storm's visible core. A driver may see brown dust rather than black clouds. A pilot may encounter rapidly changing winds near a runway. And a construction site may release loose material into the air. Trees stressed by heat and drought may fall more easily when the wind arrives. And utilities face several simultaneous problems because wind can damage lines, lightning can interrupt equipment, dust can reduce access, and floodwater can reach underground systems. Extreme heat keeps electrical demand high while crews attempt repairs, and the storm creates the outage. The heat determines how dangerous the outage becomes. A broader historical event reveals the opposite end of the monsoon spectrum. From July 21st through July 26th, 2021, Arizona experienced repeated rounds of thunderstorms and heavy rain as a strong upper-level disturbance moved through deep monsoon moisture. Large parts of the state received more than 2 inches of rain, and some locations exceeded 5 inches. The pattern eventually produced sustained cloud cover and genuine regional cooling. Phoenix recorded 3 consecutive July days, with afternoon highs in the low 80s, the first such sequence in the city's recorded climate history. That was real heat relief. It arrived with widespread flash flooding, more than 51,000 cloud-to-ground lightning strikes across Arizona, hundreds of hydrologic and thunderstorm alerts, and repeated wind impacts. The 2021 event is not a forecast for August 2026. Its purpose is to define what true replacement would require. A few isolated storms do not end a heat episode. A widespread, persistent pattern of cloud cover, rain-cooled air, and altered circulation can. The current forecast does not show that kind of immediate regional transition. Phoenix forecasters expect storms to remain concentrated over higher terrain for much of the week, with lower desert chances improving later. At the same time, high pressure is expected to strengthen again, and temperatures are forecast to climb. And that combination favors interruption rather than replacement. The current heat can be briefly dented by clouds or outflow. It is not removed from the regional energy balance. This is why the deep red heat risk map can return so quickly. The desert floor remains hot while nights stay warm, moisture reduces evaporative cooling, and high pressure rebuilds overhead. The body carries stress from the days that came before. A forecast high that falls from extreme to merely very hot can create psychological relief before physiological relief exists. People respond to comparison, so a temperature of 110 degrees can feel better after 116, even though it remains dangerous. A cloudy evening feels cooler than a clear afternoon, yet it can still carry a very high apparent temperature. A gust front can feel like the heat wave has broken. The ridge may be back in control by the following day. The most dangerous moment can be when the headline changes faster than the hazard. And what happens next depends on whether the moisture deepens faster than the ridge rebuilds. Forecasters will watch dew points first. A rising dew point shows that more low-level moisture has entered the desert air. That moisture can increase apparent temperature, support storms, and limit nighttime cooling. It is one reason. A lower thermometer reading does not automatically produce lower heat risk. They will watch precipitable water, which estimates the amount of moisture available through a vertical column of atmosphere. A high value does not guarantee a flood. It means a storm that forms has more water available to convert into rain. They will watch the placement of the subtropical ridge because storms often travel around its edges. And if the ridge remains centered too close to the lower deserts, sinking air can suppress widespread convection while temperatures rise. If it shifts far enough north or west, easterly flow can carry storms and their outflow boundaries from the mountains toward Phoenix, Yuma, or southeast California. And they will watch steering winds above the surface. Weak steering can allow storms to remain over one drainage and produce localized flooding. Stronger easterly flow can help storms move into lower elevations, but it can also extend the corridor of damaging outflow and dust. They will watch overnight temperatures. A hot afternoon is dangerous. A hot night prevents recovery. The forecast from NWS Phoenix keeps that concern active through the week. Extreme heat warnings remain in effect across the lower deserts through Friday, and temperatures are expected to dip only slightly through Wednesday and then climb again late in the week. Humidity increases the apparent heat, while widespread major and areas of extreme heat risk remain possible. And that current status directly contradicts the phrase, "the heat is ending." The heat is being interrupted. The interruption may be brief, and storm chances across the lower deserts improve toward the end of the week and weekend, but the forecast does not guarantee a widespread cooling monsoon outbreak. Some places may receive beneficial rainfall, and others may receive wind, dust, lightning, and only a trace of rain. The highest rainfall can occur in a narrow area while a nearby neighborhood remains dry. And the strongest wind can arrive before the rain. The flood can travel into a wash after the parent storm weakens. The heat can return the next afternoon. This is why the final script keeps 3 clocks separate. And the heat clock measures how long dangerous daytime and nighttime temperatures persist. The moisture clock measures how quickly humidity increases and how much storm fuel becomes available. And the storm clock begins when convection forms and starts producing outflow, lightning, rain, and runoff. Those clocks do not start or stop together. On this forecast, the heat clock is still running while the moisture clock accelerates and the lower desert storm clock becomes more active later. The map turns red because heat risk integrates the first 2 clocks even before the third produces widespread rain. And that integration is the hidden value of the product. It keeps yesterday's exposure and tonight's recovery inside tomorrow's risk picture instead of treating each afternoon as an isolated event. That does not mean every red location experiences the same medical impact, and heat risk describes potential impact at the population level. Access to cooling, housing quality, work exposure, age, health, hydration, medications, and the length of previous heat exposure all change individual risk. The product is guidance, not destiny. It is also not a substitute for official warnings. And NWS heat alerts, flood watches, flash flood warnings, dust storm warnings, and red flag warnings each carry different meanings and actions. The safest response depends on the hazard in front of the person. And during extreme heat, the priority is effective cooling, hydration, reduced exertion, and checking people who may not have reliable air conditioning. During a dust storm, drivers should not continue into near zero visibility. And if visibility collapses, follow official dust storm driving guidance rather than stopping in a live travel lane with lights that may attract other vehicles. During a flash flood, do not enter flowing water or a flooded low crossing. Water depth and road condition are difficult to judge, especially at night. These actions belong to different alerts because the hazards behave differently. The documentary should not compress them into one generic warning. The title's deep red also requires discipline in the thumbnail, and if the visual use is heat risk, it must show the product name, legend, and valid date. It should not place floodwater beneath a heat map as if the red category predicts inundation. And if the thumbnail uses storm imagery, the storm should be labeled as a conceptual transition or a historical example. No source support showing the entire Southwest beneath one guaranteed flood event. No source support saying the heat wave has ended everywhere. No source supports describing every monsoon storm as dangerous. The supported warning is narrower and more useful. A short decline in temperature can create false confidence while humid heat, warm nights, and renewed high pressure keep the health risk elevated. Monsoon storms can then add fast-moving local hazards without providing broad or lasting relief. That is the publication boundary. Every alert Valid time and map must be rechecked immediately before the video goes live. The atmosphere is not replacing one emergency with another, it is stacking them. Picture Phoenix near sunset after the day's temperature has finally begun to fall. Clouds rise over the mountains east of the city. The air smells wetter. A red heat risk map still covers the lower desert, but the sky looks different enough to suggest the heat wave has broken. And far away, a thunderstorm collapses, and although its rain never reaches the city, its wind does. And a brown wall begins lifting across open land. The temperature drops several degrees as the gust front arrives, and drivers feel the first cool air in days. Then visibility falls, power flickers, and the humidity remains after the dust passes. By morning, the streets are dry, and the ground is still warm. High pressure is strengthening again. The map returns to deep red not because the storm failed to exist, but because it was never large enough to replace the heat. It only arrived on top of it.